Oh, hello everyone. Welcome to CPP Valley. So, I am starting a series on different concepts which are used in the HFT industry, and we will try to go slow, pick one concept, understand it very deeply, understand it from the code perspective, and then we will deep dive into the internals and then the CPU architecture, and then actually try to understand how the architecture is behaving in a certain way. Okay. So the first topic that we are picking is false sharing. Okay. So let us understand false sharing by building the intuition. Okay. So there are a lot of book which you can read and understand, but since I am sharing my knowledge, I will share in a manner that it comes to you intuitively rather than memorizing it. Okay. So just let us start. I will use my pen. Mm, let's use red. No. Let's use black. Uh, let's use red. Okay. So before understanding false sharing, just one very naive concept. So our computer has RAM. So we have a RAM. Okay. Then we have a CPU. Okay. So we have a CPU. Now the CPU is much faster than RAM. Okay, so the speed at which CPU operates it much faster than RAM, which means CPU would not want to communicate with RAM every time. Okay, CPU must have some alternative to work with, and since RAM has the memory, right, and CPU has the compute power, so whenever CPU wants some values from the memory, it will not go and ask the RAM for the values, and that is why we have small memories, faster memories, which are called cache. And in cache also we have different type of cache based on their levels and based on whether they are shared among the different cores or private. Okay, so just one more thing. So we can have a CPU with multiple cores. Okay, so let us say, let us directly draw the cores. Okay, so let us say this is core 1, this is core 2, and this is core 3. Okay, I will remove it from here and I will place the RAM here. Okay, now each of the CPU will have a faster memory, and CPU will use that memory to work to do the compute operations. Okay, so we have for C1 this cache, for C2 this cache, and for C3 this cache, so on. If there are other cores, it will also have this cache. Then we again have cache, this is cache, this is cache. Okay, now this is CPU, this is level 1, and this is level 2. Okay, so these caches are called L1 cache, these cache are called L2 cache. Okay, and then we have a L3 cache also. Fine. Now this L1 and L2 are private to C1, So I will just do like this. I will mark the boundary that these L1 and L2 for each of the core are private, and this L3 is shared among all. Make sense? Okay. And even these L1, L2, L3, even these are not fast enough that they can work with CPU. CPU is even faster than these caches, and that is why whenever CPU has to do some operation from the cache, the CPU loads into its own register, and the register sits on the CPU. It is closest to the CPU. So I'll say that okay, this is the register for this CPU core. This is the register, and for this is the register. Okay, so this much is making sense, right? This is pretty much straightforward, the cache architecture. Okay, now let us understand what is a cache line. Okay, so let us say that the CPU has to pick or read some values. Okay, so let's say you have your code and there is a variable int x. Now CPU will not fetch just one variable. So let's say the memory mapping is here, this is x, and then we have other blocks. Okay, so CPU will not only read just this, CPU will read a block of 64 bytes. Okay, so 64 bytes, and this 64 byte we call a line. So CPU will load all the 64 bytes at once into its cache line. So the cache, let's say L1 cache of C1 CPU, is further divided into cache lines. So a CPU can have multiple cache lines, and the size of each cache line is 64 bytes. Okay, so now this is loaded here. Okay, so if we have something like, let's say you have a, let's say, struct a and then int a, let it be s, and then int b. So now CPU will not only read a, but it will also read b, and along with that the complete 64 byte, and both a and b are now here. A, b. I hope this is clear, right? So what happened? So both these variables a and b are sitting on the same cache line. Okay, so the L1 cache of C1 core has both the variables. So both these variables, although they are different variables, they are sitting on the same cache line. Fine. So this is normal. This is not an issue, and this is normal because let's say C1 is first working with A, then obviously A is here, and if now CPU has to work with B, then C1 will not again come and load B, and that is why it already loaded, it already prefetched 64 bytes. So B is already here, right? And so this concept is also called better cache locality. Okay, so that we'll see later. The topic of concern today is false sharing. Okay, now let us continue. So now let us bring threads in the picture. Okay, so let's say we have two threads running. The one thread is running on this T1 core, and the another thread is running on T2 core. Okay, now since they are on different cores, they will run parallelly, and this is true parallelism. They will not run in time sharing basis. This is true parallelism, right? Because they are different cores. Okay, now let us understand briefly a key concept that will help us to understand fault sharing much better. Okay, and yeah, and the concept is, sorry, the concept is cache coherence. Okay, so now understand what is the need of cache coherence. Okay, so until now, this T1 thread of C1 core which read this and fetched 64 byte on the line of this L1 cache. Now let us assume this T2 core also read the variable b. So it will not only read b, it will read the whole 64 byte. So now the cache line of C2 core will also have a and b. So now you see there are a copy of this struct s which is a and b on both the C1 and C2 cache line. Okay, so C1 also has a copy of A and B, and C2 also has a copy of A and B. Now, if one of the value changes, how does the other know? So, we need some kind of coherence protocol, right? And this concept itself is called cache coherence. And so, we use a coherence protocol. And which coherence protocol we use? We use MESI protocol. Okay. Okay, so MESI itself is a topic in itself, but I will explain it briefly enough so that you understand the context and try to relate it back to fault sharing. Okay, so I stands for meaning meaning a cache line has become invalid. It is not useful anymore. Okay, so I stands for invalid state, meaning C1 core will say my cache line is invalid. It is not updated, so I cannot use it. Okay, then we have a shared. Okay, so the current state that C1 and C2 has is shared. Okay, the copies of A and B are both same on both the cores C1 and C2. So right now the state is shared. Then we have a M for modified. Okay, it means I have modified it. Hence, only I have the ownership of this cache line. Okay, this is for mod. And then the last one is, this is E, which is exclusive. Okay, and this also is similar to modify, but it means that only I have it. I mean, only one of the core have it, but it is not changing, meaning this is exclusive to me. So for now, just forget about E. Just understand that invalid is there, shared is there, and modified is there. Now let us continue our discussion on fault sharing. Okay, so until now, so right now what is the state? C1 has loaded cache line L1 and C2 has the same cache line in its own L1, right? So right now both are shared, both have same values. Now comes the culprit. The culprit of a multi-threaded system is write operation. So write means changing the value in memory. Okay, now before you write something in memory, let's say C1 wants to write something in memory, then C1 will say that C2 also have a copy of this, and if I write it, if C1 writes it but C2 has a different copy, then it will become inconsistent, right? So C1 says that I want to modify this cache line. Hence, the other C2, the other core, the other thread where the same cache line is sitting, they have to invalidate their copy. Meaning, they have to mark their cache line as useless because now their cache line have some stale values. So you understand what happened, right? So let's say when C1 this modified, so now understand the MESI protocol. C1 modified the cache line. Okay, so C1 modified and the value has changed. Let's say it has changed the value of A. So C1 changed the value of A. Now the cache line of C2 is invalid. Okay, sense? So invalid means it cannot use it anymore. I mean, if it wants, sorry. So now if C2 has to, let's say, do some operation on B, then it cannot do operation on B because cache line as a whole is invalidated. Cache line as a whole is not usable. That is a problem, right? Because you are sharing cache line. Had A and B were on different cache line, then this problem should not have happened. But now that they are on the same cache line, T1 updated the value of A, and since they are on the same cache line, the whole cache line got updated, right? And hence the cache line of another core got invalidated, got stale, got not useful. Okay, now understand when T2 wants to write something to B. Now what happens? Now this is important. This is where fault sharing comes in picture. So C2 will say that, okay, this might not be the updated value, so just give me updated data. So C2 says that I want to write something to B, but since B sits on the same cache line as A, so I want the ownership of the cache line before I can make the changes. Okay, so C2 will send a request that give me the latest copy. Okay, give me the latest copy and also give me ownership. Now understand, ownership and copy. Okay, so C1 has the updated data, it will go to C2, and through coherence the the C1 had in L1 core, and through coherence we have a L3. Through coherence, let us just, this is an abstract view of coherence. Through coherence, C2 L1 cache will also get the copy. Okay, T2 got the updated copy. So till now coherence is done, but T2 is saying that I have to update B. It means now T1, you please invalidate your cache because now I'm going to update the value B, even though T1 is concerned with A and I am updating B, but since they are on the same cache line, the whole cache line has to be invalidated or marked useless by T1. Okay, so now T2 will update B, and so now T2 will have the latest updated cache line. Okay, so what is your observation here? What has happened? So one thing that happened is the cache line has moved from one core to another core, and now if they are subsequent write on A again by T1, then again it will move here, again it will move here, and again it will move here. So it is a ping pong operation that is happening. Ping pong is happening. The ownership of cache line is changing. There is frequent invalidation happening. There is frequent cache coherence happening. Okay. So even though the variables were different, but since they were on the same cache line, and hence it caused unnecessary interference. Right. So you now understand, right, that when the cache line is transferring between cores, there must be some data path, a bus through which the transfer is happening, right? And if that transfer is happening through a bus and it is happening like million of times, obviously it is going to cost us time, right? Okay. And one more very important observation. So consider that both the core are trying to write, then at a particular time only one thread is writing. Reading is fine, both thread can read it. For that they don't need to invalidate each other, cache lines. But if you see, at a particular instant only one thread can write, then what is the use of having multi-threading and having true parallelism? These were different threads on different cores. This is the best scenario for true parallelism. Otherwise, if you have large number of cores, let's say if you have 3 cores and 10 threads, then it is concurrent operation. That is not true parallelism. But right now, even though when you have true parallelism, you are not doing the write in parallel. You are doing a write in serial manner, right? Because at one time only one core can modify the state. So this is also why it cost us time. And in HFT, in a hot loop is something which which sits in the CPU for the long duration. Okay, so it basically is a logic which runs for a large amount of time. So in hot path, if you have something like false sharing, then it is going to like affect your business. If a user is trying to place a buy order, and in that path if you have something like false sharing, then there is going to be inconsistency, the money is going to be lost. Okay, and now let us understand then what is the solution for this. So just by looking at this, we can say that okay, so you come and you always take 64 bytes. What if after this int a I added some padding? Wait a second. So this is a right. I added some padding. So this is 4 byte. I added a padding of 60 bytes. So in total it is 64 bytes. Right. So if I added a padding which resulted in a width of 64 byte, then both the variable will not share the same cache line, right? Because the other variable will now start with here, which is beyond 64 bytes. So if we can do something like this, we can avoid false sharing. And something like this, adding padding. So how do we add pads? We use align as, right? We use aligners. So now let's jump to code. We will run 2 programs, one with false sharing. We will see what is the time with false sharing it is taking. Then we will add aligners, and then we will understand what the time other is taking. And we will also use the perf tool to understand it. Okay, so let's move to the code. Now let us come back to the code. Okay, so we will create a small program, and we will not do full-fledged benchmarking. We will use the simple time command in Linux to understand what is the real time the program is taking. Okay, and now also we might not see a lot of improvement when we use aligners. That is because the compiler does a lot of optimizations. Okay, so the version of code that we are going to write is very plain and is very simple. And but if you want the real benchmarking, which is usually written with atomics and CPU affinity and uh, uh, pinning a thread to a core, all those kind of thing, which I think is a bit lengthy, and it will take a time. Maybe in another video I can actually show you to how to pin a thread to a particular core and then use atomics to enforce cache coherence, right? And then actually reproduce the scenario that the exact scenario of false sharing, the ideal scenario. But anyway, let us run our code also. We will also see some percentage of improvement. Okay, so I am on a Linux system. I am running this inside a virtual machine on Mac. So let us write the code false sharing.cpp. Simply I will have a include IO stream. I will say that okay, I have a counter and it has x, y, okay, and then I will create the object of counter, okay, and then I'll say that okay, so there are two operations that I will be defining. In the first, I will be constantly updating uh, int x, okay, so I set it for int I is equal to 0, I is less than, let's say we run 10 to the power 9 times I plus plus, okay, so we are doing the increment of c dot x plus plus, okay, and similarly let's say we have another function t2 does not take any argument, it does the same thing but for uh, y. So I'll say that int I is equal to 0, I is less than I 10 to power 9, okay, and I plus plus, you have to do c dot y plus plus, okay, this is done. Now create our main function, let's say return 0. Now we need to launch two thread, okay, so let's say we have thread t1 and we bind it to t1 and we have thread t2 binding to t2 function, and then we have to join it also, because if your program ends but threads are still running, then that will cause terminate, okay, so let us join them. T2 join, okay, so we are using threads, right? So for thread we need to use include thread, okay, so this is C++11 threads. I hope there is no compile time issues. Counter, so let's try to compile this. So I'll say I will not use any flags, fancy flags. I will just say false sharing, and I will say this is the problematic dot out, okay. Okay, let me see at once. See. Fine, let me fix. Thing namespace STT, that is there. What else? This is here. Okay, let us compile again. Okay. T2.join. This is expected before token. I don't know, I have got blind, I think. Okay, so now we have this problematic. Now let us copy the same file. Let us create with Alignas, okay, so I'll just do this false sharing with Alignas. Only one update that I'll do is I will add padding. So I'll say that alignage of 64-bit, you add the padding. Okay, and here also we add the padding. Now let us see what happens. Let us run this also. So this is the fixed. Okay, so now we have two files, fixed and problematic. Let us first do the timing analysis of problematic. So time, and we will run the problematic. Let us try to see what is the real time it is taking. So it is taking something around 2.4 seconds. Okay, now let us do for the fixed thing. Let us see. Okay, so now it is taking 2.43. okay, so 0.01. okay, I mean there is some improvement. Okay, so in the real we have some improvement. The percentage is not much, but for this smaller benchmark this is fine. And also we are not actually reproducing the fault sharing issue. The compiler is optimizing a lot of things, even though we see some improvement, right? Because an improvement of 0.01, uh, here it may not look massive, but believe me, it makes a lot of difference. Okay, so I think this is all for this topic, and in the next video I will pick another HFT topic. And so in a similar manner we will try to cover all the topics so that you can get ready for a HFT profile, systems profile. And these concepts are not just used in HFT, these are very much system specific. So it will be asked in interviews of Adobe, even Google infrastructure, uh, then in different EDA companies like Synopsys, Siemens, Ansys. Okay, so yeah, I think that is all for today. Thank you guys.